Hello everyone. In this video I am going to show implementation of breadth-first search algorithm. Given a graph G and a distinguished source vertex S, breadth-first search systematically explores the edges of G to discover a vertex that is reachable from S. It computes the distance from S to each reachable vertex, where the distance to a vertex V equals the smallest number of edges needed to go from S to V. Breadth-first search also produces a breadth-first tree with root S that contains all reachable vertices. The algorithm works on both directed and undirected graphs. Starting from S, the algorithm first discovers all vertices with distance 1, then it discovers all vertices with distance 2, then all vertices with distance 3, and so on, until it has discovered every vertex reachable from S. Breadth-first search uses a single first-in first-out queue containing some vertices at a distance k, possibly followed by some vertices at a distance k plus 1. The queue therefore contains portions of two consecutive waves at any time. To keep track of progress, breadth-first search colors each vertex white, gray or black. All vertices start from white, and vertices not reachable from the source vertex S stay white the entire time. A vertex that is reachable from S is discovered the first time it's encountered during the search, at which time it becomes gray, indicating that it's now on the frontier of the search, the boundary between discovered and undiscovered vertices. The queue contains all the gray vertices. Eventually, all the edges of a gray vertex will be explored so that all of its neighbors will be discovered. Once all of a vertex edge have been explored, the vertex is behind the frontier of the search and it goes from gray to black. Breadth-first search constructs a breadth-first tree initially containing only its root, which is the source vertex S. Whenever the search discovers a white vertex V in the course of scanning the adjacency list of a gray vertex U, the vertex V and the edge U, V are added to the tree. We say that U is the predecessor or parent of V in the breadth-first tree. Since every vertex reachable from S is discovered at most once, each vertex reachable from S has exactly one parent. With one exception, its root has no parent. Our graph is represented using adjacency list. We can see example adjacency list in the current picture. It consists of an array of numbers of vertices lists, one for each vertex in V. For each vertex U, the adjacency list A of U contains all the vertices V such that there is an edge UV belongs to graph edges. For example, fourth array element is a list of edges for vertex number 4. These are 2, 5 and 3. Now let's take a look at the code. The project is a C++ console application, and as an IDE I used Visual Studio. The main part of a program is the declaration of a class representing our graph. A graph class contains two public fields, head and var. Var is a pointer to pointers of vertex structure. It represents vertices of a graph. It includes ID field, which is the number of a vertex, color, which can be white, gray or black, distance, which is integer distance from the source vertex, and finally a pointer to predecessor vertex. Second field in the graph class is head, which is a pointer to pointers of a node structure. It represents a node of a linked list representing the graph. It contains of a pointer to vertex and pointer to the next node. Next, we have constructor of our graph class. It takes as a parameters vector of edges, integer n, which is the vector size, and capital N, which is number of vertices. Here, edge structure represent an edge with start vertex and end vertex. Inside the constructor, we initialize head and var pointers. Then uppercase n and lowercase n. Then we assign all elements of head and var to null pointer. Further, we have for loop that iterates on all the edges. If begin and end vertex of an edge is null pointer, we create these vertices. Next, we create new node by calling function get adjacency list node with parameters end vertex number and head of structure vertex number. Here we create new node and initialize it var field to var of end vertex and its next field to current head. Then we assign new head to point to the newly created node. The structure of a class graph releases all dynamic memory of head and var. Finally, we have our breadth-first search algorithm defined. It takes as a parameters our graph and source vertex. In a for loop, we have initialization of all graph vertices other than the source to color white, distance max int which acts as infinity, and predecessor to null pointer. The source vertex we color gray, distance to 0, and predecessor to null pointer. Then we declare Q and push a source vertex to it. Next, we loop until Q is not empty. We take vertex from the Q front and pop it from the Q. In first iteration of a while loop, var_num variable will be our source vertex. Then as variable we initialize with linked list of head of vertex popped from the Q, so we have access to all vertices adjacency to var_num vertex. Below that, we iterate on all adjacent vertices of a var_num, and if its color is white, we color it gray, its distance assigned as parent distance +1, and its predecessor to parent. Then we push it to the Q, and finally we assign S to current S next, which points to next vertex in a linked list. After we visit all child vertices, we color vertex popped from the Q black. Now let's take a look at main function. In its first line we have vector of edges defined. Then we construct a graph. After that we display it as an array of linked lists. Then we call our breadth-first search algorithm. After that we print distances to all vertices from the source vertex. And finally print path from source which is 0 to vertex number 5. Functions that print graph information are defined in our graph class. Now let's run this program and see the output. At the top we have our linked list representation of a graph. Then we have distances to the source from each vertex. And at last we have path from vertex 5 to vertex 0, which is our source. We can verify that all the output are correct. For example, we see that vertex number 3 is connected to 6 and 4. Distance from the source to vertex 5 is 4. And path from vertex 5 to 0 is 2, 4, 3, 0. You can download the source code from GitHub and change edges of a graph and see how the output changes. GitHub link is in the description. That's all. Thank you for watching.